Welcome everyone, my name is Jacob and I brought you the paper Test Intelligence, How Modern Analyses and Visualization in Teamscale Support Software Testing Today. In my business life, I work for the company CQSE. That is short for Continuous Quality in Software Engineering, and one thing I do there is to support teams in their development efforts and testing activities by using data the teams already have. This is also where we land the term test intelligence from. So it's not related to artificial intelligence or machine learning. It is from the term business intelligence, where you have some data sources and you do data analytics to find out how your company basically works. Today, we will focus on analyses and visualization of those, use the version history from the version control system, tickets from the bug trackers or issue trackers, and test coverage from your test runs. Questions that can be answered from analyses that are within test intelligence are usually asked by testers or test managers and go in the direction of where are untested changes, because it is most likely that bugs occur there in production. Where do the most bugs occur in my software system? So are they all in one module or different modules? And can I take some countermeasures against those bugs? And regarding the test execution, are there maybe tests that are more valuable than others to execute right now? I brought you now some examples for the different data sources, and we will start with an example from the version history. So you might know this picture. This is a simple file diff, so same file in two different versions, and the differences are highlighted by a gray background. This is a low-level approach to view the changes, and I can take that to a higher level using a visualization. And therefore I use a tree map right now. A tree map displays or visualizes a tree structure, in this case the file and folder structure of a software system. And here a large rectangle with a white border represents a software component, for example, a Java package. If I zoom in one step, I get all the files, all the classes of a system. And if I zoom in one further, I get all the methods. And the size of a rectangle here directly corresponds to the length of the method in terms of lines of code. And now I can visualize the changes by saying, from a given start date, if the method has not been changed, I want to display it in gray. If it has been changed, I want to have it in color, and I use orange for methods that have been changed and red for methods that have been added to the code base since the start date. Next data source is test coverage. You also might be familiar with it. In this picture, if you execute tests, you can record which lines have been executed during the test, and for this method I brought you, all lines have been executed but one. This is also a low-level approach to investigate code coverage, and I put that to an upper level by displaying it also in the tree map. Same tree map as before, or same tree map layout, but now the color semantic has changed. All methods in gray are methods that have not been executed in the test, and the green ones are those that have been executed in the test. Without a cool visualization, but for the sake of completeness, I brought you an example for the last data source, so a ticket from our issue tracking system. This is a screenshot from our Jira, and it has a ticket ID, it has a description or a title, then a longer description on what is the ticket about and some meta information. From the data sources to the actual visualizations. The first visualization I want to show you is the visualization of a system-wide test gap analysis. Test gap analysis itself focuses on showing you changes that have afterwards not been run in the tests. Why is that relevant? Our intuition says to us, and also research has shown, that the probability that you will have a bug in such an area, so a changed yet untested area of the software system, is higher in production than for the other areas of the code. So we already have all the ingredients that you need for that analysis. So we have the changes tree map from before, we have the execution tree map from before, and to now get to the results of a test gap analysis, I just take the changes tree map at the bottom and lay the execution tree map above, ignoring all the methods that have not been changed. The results would look like this. So all the methods that have been changed and tested are displayed in green, and those that have been changed or touched and not been tested remain orange or red. And this analysis here revealed large areas of the code not have been tested after the last modification or addition to the code base. So in fact, this is not just a made up or fake system. This is a real software system right before the planned release. And we asked the team whether this is intended, that there are so many of the changes and additions not tested. And they told us that it's not intentionally, but they had some innovation project where they wanted to add automatic tests, software tests to the project. And somehow there was a misunderstanding between the departments of the automatic tests and the manual tests that have been performed earlier. And somehow these areas were remained untested. They decided to shift the release based on that results and add another phase of retesting, and afterwards most of the test gaps were closed and appear now in green. Such a big tree map might be overwhelming, so it shows you a lot of information if I'm just responsible for writing automatic tests for just one single issue, or if I'm the tester responsible to test a single new feature or a bug fix. And I brought you an example. So how we develop today, it is not pure waterfall, but agile, and we work on different feature branches and release several times a year. There's the possibility to not view all the test gaps of a system, but to view the results just for a single issue. And this is how we apply that in our own development. So this is also a screenshot from our own development. You have in each row one single ticket. And on the right hand side, you see a bar chart that says you how much test gaps is there still remaining. If I click on one of the tickets, I can also investigate where are the remaining test gaps. This tree map only shows methods that have been altered within that ticket. And we can do that by prefixing each commit that is done for one issue with that issue ID. The next visualization can reveal interrelations. And I brought you an example to show interrelation between coverage, code coverage, and fixed frequency. This tree map here shows you all the files of a software system, and the opacity of the blue color shows you how often has this file been changed in course of a bug ticket. So we only counted bug tickets here. Tickets that were classified as feature tickets were not taken into account. And you see this middle area of the code base is somehow striking because it's much darker. And let's see how this looks like if we take this tree map here. This is the tree map of the line coverage, and also the middle area is striking. And white means a low code coverage, green means high code coverage. And if we take that over each other, both tree maps, it indicates some kind of interrelation. We also went this time to the team and asked them, why is that the case? And they told us that the middle area is standing for the UI code, and the UI code were not good testable. So developers wrote less UI tests as the UI tests were difficult to write. The project managers decided to invest additional time to improve on the testability of that code, and hopefully now also the fixed frequency in the UI code is lower. The next visualization shows you how you can benefit from the test selection on the basis of code changes and coverage. If you have a test suite that runs over a long period of time, it might be good to select only the tests that run over changes, because it is most likely that those tests who run over changes will find bugs early, and you can also feedback to the developers very early that with their changes maybe some things in the system broke. To demonstrate that, I brought you an example from our own development. Those are the changes we have performed for one single issue. And to perform test selection, we need test coverage per test case. So not for a whole test suite, but per test case. And this is how the recording for one of our test cases looked like. I will now show you an animation that runs 30 tests per second, and each coverage from one test will light up in white and then fade out to green. And we will see how fast we will execute one of that changed methods. So when we look at that animation, we see some areas of the code lighting up more than once. So these are tests that, or these are areas that are covered by more than one test. But even if we have executed by now some 100 tests, the changes have not been covered yet. And the probability that we will find a new bug there is very low, since we have not run the changes. At the end, it was that we have had more than 4,000 test cases executed, but only 1, 2, 3, 4 test cases did cover any of the changes. And this is how the test selection algorithm works. We also use with some teams. We select the tests first that run over changes. Besides test selection, also test prioritization plays an important role when it comes to long-running test suites. And I brought you a visualization that shows you the benefits of test prioritization based on additional coverage per time. This chart shows you how the coverage evolves during the runtime of your test suite. So on the right, on the x-axis, you see the relative runtime of your test suite, and on the axis, you see how the coverage evolves. And in the normal execution order, you see a rather flat curve, and on the orange curve, you see an optimized run order, and there the coverage is gained much faster or increased much faster. So why can we do that? I brought you an example with the project Pixelitor, which is an open source drawing application implemented in Java. Also for Pixelitor, we recorded each test case one by one, so we have coverage for every single test case. And if one wants to compare the different test coverages, you will see that the first row here looks somehow similar, and the last row compared to the first row looks more different. In a normal test execution order, you execute mostly tests in buckets. So tests that are testing similar things are run right after each other. And we see that also in Pixelitor. So we have different blur operators in Pixelitor that make your picture more unsharp. And the first one that would be executed is the Gaussian blur filter. You have the coverage of that test case here. The next test case executed is the test of the motion blur filter. And you see again the coverage of that test case here. But the blue methods are those methods that have already been executed by the first blur filter test. So if one would have introduced a bug in one of the blue methods, it's highly likely that the first test would have already detected that bug. And only the green methods here are additional coverage for that test case. This holds true for the next test case, the lens blur filter, also not that many green methods that are additional executed, and also for the smart blur filter. So if you want to optimize that, we can do it in a different way. So we select the test case first that covers the most methods in the system in the least amount of time. This would be this test case here. And next we execute the test case that executes the most additional methods in the least amount of time again. And you can see also here some blue methods are there, but the number of green methods is much higher. So you gain much faster your test coverage in your test runs. Also the third test covers a lot of new green methods. This is how we can obtain coverage much faster in a test run. And in many teams, we see also the wish that they just want to have a clear cut. For example, like after 10 to 20% of the normal test run time, for example, just like 1 hour instead of 10 hours test run time. So this would be a clear cut here. And you see if you optimize your test run order, you would get more than 60% coverage. And for the unoptimized one, you would only remain with 20% method coverage. This is also an interactive chart. So if I select 7 seconds of runtime, I would get the results here for executing 3 tests. With 12 seconds, I see that I should execute 5 tests, and you can see in the chart above how much coverage you would gain with executing those tests. In the paper, we present additional visualizations, but for the sake of time, I only want to show them briefly here. We introduce you to auto-generated verification matrices. So for each requirement, we can answer with that visualization whether there exists a test that verifies that requirement, and if there is a test, whether it actually succeeds. Another visualization we show is if your test fails, you might be interested in which methods have been changed since the last pass of the test, as it's most likely that the failure of the test case might lay within the changed methods since the last pass. Last visualization, also just briefly, is the test selection of test cases that can close a current test gap. So this is the issue test gap tree map we have seen earlier, with 2 methods already covered and 3 methods that are a test gap. And this method here on the right side could be covered by executing one of those 2 tests here. This was a lot of information in not that much time. If you have any follow-up questions, either today in the workshop or later on, just ask me, write me a mail, call me, and we will catch up. And I'm happy if you read the paper. And now I thank you for your attention, and I'm open for any questions.